All right. Good morning, everybody. It's Jay Wolf. I am with Big Brothers Big Sisters. And today I'd like to welcome you all to our lovely Discovery Fest, our final day. We have the awesome presenter, Kevin Dilley, and he'll be sharing with us and just kind of delving more into the sciences and enticing our kids to get more into STEAM. So Kevin, I will go on ahead and share our video over to you. And thank you for joining us today.
Thank you so much. It's not letting me start my video.
You'll need to make him a co-host, Jay.
All right. All right, are folks able to see me? There we go. All right, good morning, everybody. Wonderful to have you with me. My name is Kevin Dilley. I am from Explora Science Museum. I'm here at the museum right now, and we're gonna do some fun stuff today. I've got a lot of different demos for you. We'll talk a little bit about the science behind it. So let's just jump right into it and get started. So let's start out with a little bit of chemistry, okay? So I have here something that I think is pretty interesting, actually. This is something called a stir plate. And with this, I have a little magnet here. I can put it on here. If I turn it on, there's a magnet underneath the plate here. If I turn it on, I can get it to start turning. Oops, hold on. Oh, it was just working. What's going on here? Okay, technical difficulty. Let's move on to the next thing then. That's all right. So let's look at an interesting thing called phenolphthalein. So phenolphthalein is something that is a pH indicator. So it's something that can show us if something is an acid or a base. So let me grab just a little bit of it right here. All right, so here it is. I have this phenolphthalein. It's a clear liquid, and I'm going to use it to paint with. And so let's see what happens when we paint with our phenolphthalein. So I have some more here, some phenolphthalein. I'll put some into a jar and into my beaker. And I'm going to paint with it. So we'll do this here. Let me paint a little bit on here. Okay. And so we can see that it's just a clear liquid. So if you put something on a piece of paper and it's clear like that, you might be able to see a little bit of it as it's wet, right? You can see that it's wet there, but we can't really see all that I wrote on there. But let's put something on there, see if it will do anything to it. So I have here some Windex, so just some window cleaner. And I'm gonna spray it on here. And let's see what happens when we spray this window cleaner onto my phenolphthalein. Here we go. There we go. So we can see that with this window cleaner, it's a blue liquid, right? But look at what it's doing to my little sign here that I drew on, right? So there's my Big Brothers Big Sisters sign. And so what's happening here is our indicator, our pH indicator, that phenolphthalein chemical, it can tell us if there's an acid or a base nearby. And in this case, we're looking at window cleaner, which is a base. And so we can see that this clear liquid, when there's a base that comes in contact with it, we see that it creates this bright pink color. And so we'll set this off to the side. We'll let it dry off. As you can see right now, even as it's drying off, it's starting to fade some. We'll let it dry off some and then check later and see if we can get it to turn pink again. So this one turns pink whenever it comes in contact with a base. Let's look at something else. So that is phenolphthalein. So it's a chemical that we can create to be a pH indicator. But there are some pH indicators that are natural. So ones just occur in the world around us. And one of those is cabbage, actually. So if you take a red cabbage and you boil it in a pot of water, that water can take on that purple color of the red cabbage. And this is what that is. So if you just boil it for a while on the stove, you'll get this juice. So this cabbage juice is something that you can make at home. And we're going to use it to test out some different materials and see how cabbage juice responds to acids and bases. So I've got here some beakers. So I'll pour some into 3 different beakers here. So we can see it has this purplish color to it. There we go. So I've got 3 different ones here. And now let's try and add some different things to it. So let's try and add some bases, let's add some acids, and let's see what happens to our cabbage juice as we do. So the first thing I'm going to add is some vinegar. So let's see what happens when we add some vinegar to our cabbage juice. So I have some vinegar here. Put a little bit of vinegar in, and we'll see. So vinegar is an acid. And so let's see how our cabbage juice reacts to an acid. So as I put this in. So you at home, you're going to be my lab mates here in my chemistry lab. So as scientists, one thing that we do is we make observations. So we want to make sure that we make good observations. So notice what's happening, see what types of changes happen, if any changes happen, or if they don't. So let's add a little bit of vinegar in here to our purple cabbage juice, and let's see what happens to it. So I put some in there. Let me just stir it around a little bit, and you can see that there is something happening. We've got to change. I'll put one that doesn't have anything in it next to it as a comparison, so we can see with an acid, this one turns pink. So this is different. This cabbage juice is different from our other pH indicator from our phenolphthalein, right? That one turned pink when we had a base that came in contact with it. This one turns pink when an acid comes in contact with it. So let's see if we can make something with a base that we can add to this other one and see what happens to that. So I have here some baking soda. So we're going to add some baking soda to our cabbage juice, and let's see what it does. So let me mix just a little bit of baking soda and water in here. So let me just put some baking soda into this beaker. Okay, so I've got some baking soda in there. Let me put a little bit of water in here. Mix it together. And so baking soda is a base. And let's see what happens when we add some base to our cabbage juice here. So there we go. Get some baking soda, and let's add some base to it. Let's see what happens here. Does this change it at all? A little bit more in there. Let's see, is that changing at all. Let's mix that up some. And we'll put this one up to the screen as well. And let's see if that is any different. It's a little bit hard to see on their screen, but it is slightly bluer. So the one that doesn't have anything in it is purple. When we add an acid to it, it turns pink. And when we add a base to it, it turns a little bit bluer. There, I hope you can see that some. So it's a slightly different color. You can see that there in the light. So we can see this one changes either blue or pink, depending on if there is an acid or a base present in it. Okay. So now let's look at this and think about something else. So we know that it's going to turn pink when there's an acid. So and we know it's going to turn blue when there's a base. Let's see if we add something else to our cabbage juice, to our liquid here, and see what it does. And what I'm going to do actually is I'm just going to blow into it. So I'm going to just take my breath and blow into the cabbage juice, and let's see what happens to it. So I'm going to put it some more in here. We'll leave this one as our one that we can compare to. And let me pour some cabbage juice in here. I'm going to blow into it. And you might know already that when we breathe, we breathe out carbon dioxide, we breathe in oxygen. And I see that there's a question. Go ahead. Is there a question for you?
So Kevin, we have two questions. So one of the questions was, why did the BBBS sign turn pink instead of a different color? And then the second question is, how would you know if something is an acid or a base?
That's a great question. Both are great questions. Let's start with the first one about how we know if something is an acid or a base. And when we think about acids or bases, they talk about pH. So it's a little p and a big H. Let me just write it here on the board real quickly. So it's a little p and a big H, right? So small p, big H, okay? And this H here, this H stands for hydrogen, okay? So this stands for hydrogen. There are all sorts of different elements, different things in the universe, right? There's hydrogen, there's copper, there's nitrogen, all these different things. And hydrogen is something that's really, really important for chemistry, actually just for lots of stuff happening. And so hydrogen, when we measure pH, it's measuring essentially how much hydrogen there is in a material. So we think about hydrogen on if it can break off and either react with stuff, or if there's a lack of things, a lack of hydrogen there that will want to have hydrogen come and react with it. So when we think about pH, we're looking at how much hydrogen there is. So an acid is something that has a low pH. And so that means that there's not as much hydrogen and not enough hydrogen come and react with it. And when something has a lot of hydrogen in it, that's called a base. And so when it has a high pH, and so that means that it has stuff that can come off and react with stuff. And so when we're looking at pH, it's essentially, that's what an acid or a base is. If it can have this hydrogen that come and react with it, or things that have extra hydrogen that go react with other things. And so with our acid-base indicators, we use those to help us determine if something is an acid or a base, it reacts or doesn't react with hydrogen. So our acid-base indicators, like our big brothers, big sisters sign, like the cabbage juice, there's something in them that will change when there's hydrogen that comes and reacts with it, or hydrogen is being pulled off of it. And so that's how it changes colors. And that's why we're able to use them to let us know if there's an acid or a base present. And so let's do another test here. Let's look and see what happens when we breathe into our cabbage juice. So let's see if there's any pH change, if there's an acid or a base present whenever we do that. So I'm going to blow into this. So this is my water. It's just water with like that cabbage juice indicator. So it'll tell us if there's an acid or base in there. So I'm blowing into it. And you probably know that we breathe in oxygen and we breathe out carbon dioxide. So that's what humans, that's what animals do, that they breathe in oxygen, breathe out carbon dioxide. So I'm breathing out carbon dioxide right now and putting it into the liquid here. And let's see what happens. And let's notice what's happening to it. I'll hold it up next to this one, which is my one that I didn't breathe into. And you might notice, is it starting to turn pink or is it starting to turn blue? I want you to decide for yourself. Let me blow a little bit more into it. There we go. So now we can see that there's a little bit of a change here, right? It's starting to turn pink. So that means that my breathing into it is making this turn more acidic, okay? So it's changing the pH of the water just by adding carbon dioxide to it. And why is this important? This is important because of a lot of the stuff that's happening with global warming, right? So things that are producing global warming is that we're producing more greenhouse gases. And one of those greenhouse gases is carbon dioxide. So from burning different fuels, we add carbon dioxide into the atmosphere. And that carbon dioxide gets into the water. So just because, it's in the air, it comes around just like me blowing, adding carbon dioxide to the water, it's making it more acidic. And so this is important because certain animals that live in the water, so maybe like coral reefs or different fish or other things, they're used to a certain pH in the ocean or in the lakes or in the rivers. They've kind of developed over centuries and millennia to be able to live in this water with a certain pH. But if we change the pH and make it more acidic by adding carbon dioxide, then that can really mess with them and they might not be able to survive. So when we add more carbon dioxide to the world by burning fossil fuels, it's changing the pH of the water. So when you mix carbon dioxide with water, you create something called carbonic acid. So it creates this acid in there. So it's the same type of thing that happens when you carbonate beverages. So like sodas or seltzers, things like that, they add carbonation to it. They're adding carbon dioxide, the fizziness, the bubbles inside your drink is carbon dioxide. And so that creates carbonic acid in your drink. And that's what makes your drink kind of more acidic. So if I put some soda in my cabbage juice here, it's going to turn pink because there's an acid in the soda from the carbonation. There might be other acids, but the carbonation alone creates a small amount of acid in there. So that's a little bit about pH indicators and why it's important for us to pay attention to pH in the world around us, because we change how things are. If it's more acidic or less acidic, that can really affect how things can work or survive. Give one more test here on my stir plate. See if I can do this demo. Let me try plugging it into a different outlet. There we go. All right, so we got to work. Okay, so let's go back to this activity then. So like I said, this is my stir plate and there's a magnet underneath. There's a magnet here. If I turn my stir plate on, it will, oh no, it was just working. Let's see if we can get it to go again. All right, okay, so it'll stir. And so what we're gonna do is we're gonna put it inside of my beaker here and we'll be able to stir up some stuff. So instead of me, like, if you're cooking in the kitchen and you have a spoon and you want to stir what you're cooking, you could do that. In the chemistry lab, we sometimes use this to be able to keep stirring what it is that we want to stir over and over again, okay? So let's add a few things in here. And for this one, I'm going to put on my goggles. I want to be nice and safe here. So we're going to add some stuff here. I've got some milk of magnesia. This is some stuff that sometimes if people are having a upset stomach or something like that, this will help with that. So I'm going to pour in some milk of magnesia into my container. And you can see it's just this white liquid here. So let's pour that in there. And put just a little bit more. Okay, there's that. I'm going to pour some water in to fill this up about halfway. So I'm going to pour some water into my beaker here. All right, there we go. And let's get it stirring so we can get that all mixed up. Make sure it's mixed up. Oh, the stir plate is having problems here. Spinning. I think we got it stirring now. Going. All right, so we've got it going. And so now I'm going to add something else in here. I'm going to add something that's called a universal indicator. So this is a type of a pH indicator as well. And let's see what happens when we add some pH indicator in here with our milk of magnesia. Let me pour a little bit of this in here. And let me just show you this. It's a green liquid right now, okay? And let's put it in to see what happens with our. And notice what is happening to our milk of magnesia in there. Let me put just a little bit more in there. There we go. And so we can see that that green liquid started turning a purplish color. Okay, so it's a purplish color now. And so we can see that our pH indicator there turns purple in the presence of milk of magnesia. And I'll let you know, milk of magnesia is a base, okay? So this stuff turns purple when it's in the presence of a base. And so let's add some other things to it to see what happens when we add an acid to our pH indicator, okay? So I have here some vinegar, and let's put some vinegar. Actually, I'll take my one that I had before. I'll use my dropper bottle here. We'll put some in, and let's notice what happens as we put some acid into it. Actually, let me get my stir plate going. There we go. Now it's really stirring. Okay, there we go. So we got it stirring. Let's put some vinegar in here and let's see what happens to this purple liquid as we add some vinegar to it. Put some in here. And notice what happens to our, let me close the blinds. Getting a little bit of a glare here. So as we add some vinegar to it, we see it'll change a different color. So it turned first to pink, and then it went to orange, and then yellow, green, blue. Let it keep going. And we'll see if it goes back to being that purple color. And we can see it is kind of turning back to purple. And so what's happening here is our indicator, our pH indicator, is changing color. This one changes all sorts of different colors depending on how strong or how weak of an acid is, or how strong or how weak of a base it is. So we can see with a pretty strong base, it turns this purple color. When we added the acid, it turns this, kind of yellowish, orangish color, and we see that it's going back. So the acids and the base will counteract each other. They'll cancel each other out. So right now there's more base in there than there is acid. As I add acid, it changes the pH, but then as it's mixing, that acid mixes and cancels out the base that's in there. And we see that it kind of changes through the colors as there's less and less acid and gets more and more base in there, and it turns back to the purple. So let's add some more, and we'll let it change through this rainbow of colors. And eventually, we'll put enough acid in there to be more than the base is. So all of the base will be canceled out by the acid, and we'll just have acid left, and it will stay that yellowish color. But we can see as it goes back through, the amount of acid or base that's in there, we get these different colors, and we get this rainbow of different indications of acid or base in there. So I'm gonna just pour a whole bunch of vinegar in here, and let's check and see what happens when we have enough vinegar in there to counteract all of the base. So this acid can counteract all of the base of the milk of magnesia. And we'll see. It seems like it's staying this kind of orangish color. Looks like it's going dark. So it didn't have quite enough, right? Notice it's taken a lot longer for it to change back to those colors. So let's add some more acid.
We had a question that came up.
Yeah, go ahead.
Asking, if you don't have a stir plate, how would you mix it, and would that affect the colors? And does chemistry use a lot of math?
Yeah, definitely. So if we didn't have a stir plate, we could just stir it by hand, right? So the stir plate just makes the reaction a little bit quicker. So if I just poured it in without it stirring, it eventually would do the color changes, right? The stirring just makes it go a little bit faster. So one thing about chemistry is about having the speed of the reaction, how quickly things mix together affects how it behaves. And in this case, if we're mixing it more, then it can change colors quicker and quicker. If I just poured it in without the stirring, it will go through those color changes. It's going to just take a lot longer because the acid molecule and the base molecule have to find each other to be able to cancel each other out. So the more that we mix it around, it's more likely that they're going to find each other. If I just leave it in there, eventually they're going to kind of meander around and find each other, but it'll just take a lot longer. And yeah, definitely chemistry takes a lot of math. It's not all about math, but the math is definitely a part of it. So with this that I'm just doing with you right now, I'm not really measuring out the stuff too much, right? Or I'm not timing how long the reaction takes. But that could be something that we could do, and that would require some math in it. So I could look and see if I have a very specific amount of milk of magnesia and a very specific amount of vinegar and mix them together, I can check and see how long the reaction takes for it to go from the yellow color to the purple color. And so we could calculate those things using math. But for demo purposes, we can just put it in there and see what's happening. But maybe in a more lab setting, we might want to calculate how those things happen. And here we can see that we've got we've got more acid in there than base, and so it is staying this reddish color now. So it's not changing back. And so there we can see our acid base indicator and how that affects the color that we get from it. Let's look at a couple other things here. So let's think about that. I was just talking about kind of how quickly things react. So let's look at that and investigate a little more about how things might react at different speeds. So I've got here a couple more beakers. I have here some Alka-Seltzer. So you guys might have seen this before. So this is something that will fizz when you put it in water. And so let's check out and see how it might react the same or differently depending on what we do to it. Okay, so I've got here, there are two different tablets of Alka-Seltzer here. Okay, I've got one that's a nice round one. I've got another one that's nice and round, but let's change these things a little bit. So we'll leave one that's solid, and the other one I'm going to smash it up and make it so that it's a powder instead of a solid piece of Alka-Seltzer. And so for that, I need a very scientific tool. I need a hammer. So we're gonna pound this a little bit. I'm going to turn it into a powder. Okay, so now it's all broken up. And we have a powder here instead of just a solid piece of the Alka-Seltzer. And so we'll put in one of these, we'll put the solid piece, and in the other one, we'll put the powdered pieces. Okay, and you can see that we've got all of this. So they started out the same amount, right? We have the same amount of each one. Each one started out as one tablet. There we go. Oops, got little pieces there. Okay. So there we go. So we've got the same amount, one that's whole and one that is broken up into smaller pieces. And we're going to pour some water in there. I'm going to pour the same amount of water into each one at the same time. Okay. So let me put a little bit of water in here. I'll put, there we go. There's about 70 milliliters. Put the same amount in this one. There we go. So we got them, they're the same amount in each one. And we're going to pour it into the containers here. And let's see what happens to them. Remember, it's the same materials, right? It's the same amount of the materials. The only thing we've done is we've made one that's solid and one that's all broken up. And so let's look and see what happens to them as we add the water. So I'll just pour them in at the same time. And here we go. What are you noticing happening with our different things here? All right. So we saw with this one over here, the one that was the powder, we got a whole bunch of bubbles right away. And it looks like right now, it's kind of stopped bubbling, okay? This one over here, it didn't have that big burst of bubbles, but we see it's still bubbling. It's going a lot longer. So we can see that we can have a different reaction. It's the same type of reaction, still creating bubbles, but we can have a different rate of reaction, meaning that one will go quicker and it'll be done faster, and the other one will go slower, but it'll last longer. And so this has something to do with what we call surface area. So surface area is if we think of something and we think of how much of the outside there is that's able to react with the air, or in this case with water. If we create more surface area, so more, if we break it up, meaning there's more pieces, parts of it that the water can get to right away, then it's going to have a really quick reaction. With this one, it has a smaller surface area. It only has the outside. There's a lot of more stuff inside that's not being touched by the water. And so the water is going to react with what it can touch. And once that's used up, then it gets to more on the inside, so it lasts longer. But this one is a lot quicker because of the larger amount of surface area that allows it to do that. And so why is this important? Well, it's important with things like when we were using the stirrer, right? There's more things that can react because it's moving around, but it can also affect other things. So I've got here a powder that is called Lycopodium powder. It comes from club moss. So the spores of club moss we can get, and they're these tiny little pieces of powder. And let me just put some into a beaker. Let's see what happens when we do that. So I'll put a little bit here in the beaker. And so you can see it's this kind of yellowish powder. It's really fine powder. And let me get a lighter. And let's see what happens when we put some fire onto it. And so let me the light. So use the lighter. Okay, so I've got a lighter here, and I'll just put it in here, and we see that nothing really happens to it. It kind of gets singed a little bit, right? It got a little bit singed, but nothing big happened to it. So what we're going to do is let's try and change the surface area of what can react with this. So right now we just have kind of like a little a mound of the powder. And so that's similar to when we had the large Alka-Seltzer that wasn't ground up. But what would happen if we spread this out a lot? And we'll see what happens to this. So what we're going to do is I have a tube here with a lighter on the end. I'll put some lycopodium powder into this. I'm going to blow it out. So the powder is going to spread out into the air, and we'll see what happens with our lycopodium powder when we do that. So let me move my camera back some so we can see this. All right. So I'm going to put a little bit of powder here into the tube. So I'm going to squirt some of that in there. Okay. So I've got some lycopodium powder in my tube. Let's get just a little bit more. Okay. And now I'm going to light it, and I'm going to blow through the tube so that the powder goes flying out. And let's see what happens to it. Okay. And here we go. There we go. So you can see a big fireball happens to it. So same thing like with the Alka-Seltzer, right? When it's all squinched together, there's a lot of surface area. Just like here, it's all kind of put together. When I put the lighter in there, nothing really happens to it. There's no huge fireball, right? Some of it gets singed, but when we spread it out, it means that there's more air around each molecule. When something burns, it needs to have oxygen, and so there's more oxygen around each one to be able to get it to be able to burn, and we can get a fireball. So let's do it one more time, just so you can see, now that you know what to expect. And here we go. And so we get these big fireballs. And so this is why it's really important to think about the rate of reaction of something and the amount of surface area. So that's why it's really dangerous to have gases around. Gases can have a lot of air around them. And so if there's gas vapor, not as a liquid, but as a vapor, as a gas, then we can get some very dangerous things like this fireball here. So let's investigate that just a little bit more. And let's do another demo here. This is something called the Whoosh Bottle. And so for this, I'm going to need a water jug here. And inside this water jug, I'm going to put a little bit of alcohol. So I have here some rubbing alcohol. So this is isopropyl alcohol. And we'll put some in here. I'll swish it around. And so right now is, as a liquid, alcohol will burn, right? But let's put it in here and let's turn it into a gas like I was just talking. So I'm going to squirt a little bit in here. There we go. I'm going to swirl this around some. So by swirling it around inside the container here, it's creating a gas. So it's making this alcohol evaporate. So it's not all of it's not all of it's still a liquid. So some of it is filling up the container with a gas of this alcohol. Let me get all of this out. Okay. There we go. Let me pour out the extra liquid. Okay, so I'm just gonna pour out the extra liquid. Okay. So we don't need all that liquid in there. We just want the vapor, but I'm gonna keep it covered because we want to keep that alcohol vapor in there. And what we're gonna do is I'm gonna add some heat and some fire to this, and let's see what happens to it. So let me move this back just a little bit so we can see all of what's happening. And actually, I'm going to turn the lights off so that we can get our thing. So let me just put paper over here to keep that vapor in there. Let me turn the lights down. All right, so again, we're going to want to pay attention to what's happening in the container. So you're going to have to make observations. So notice what happens to it. And here we go. So you might have to look, and you might also have to listen to see what's going on here. Here we go. Oh no. Oh, didn't work. That's all right. Things aren't always work the first time. Let me try this one more time. Let me add a little more alcohol. Try and get some more vapor in there. Some vapor in there. Pour off the extra liquid. All right, here we go. There we go. So that is our whoosh bottle, and you might figure out why we call it the whoosh bottle. It makes this big whooshing sound to it, right? So there was a lot of noise to it, but you also saw some flames, right? So it's actually really warm, the container is, and it whooshed out. It made this big sound. You saw the flame flying up from there, and you probably saw inside the container, there were some flickers of flames inside. So what's going on with that? So same idea, thinking about how when the alcohol is spread out into this big area, there's more oxygen and air around it. And so when you ignite it, it can, all of it get ignited at the same time. Now, why did it make that big whooshing sound and the flames come out the top? That's because when things burn and there's a lot of heat that's created, it expands. So there's a certain amount of area inside this container. And when it ignited, that alcohol, that fire, that flame wanted to get bigger, expand, because it was heating up. And so the only place that it could go was out through the top. And so that whooshing of air, so, probably if you've had, the wind blowing really hard, you hear that movement of air creates sound. Same thing here, that movement of that air coming out as it expanded came out the top. But you also probably noticed that there were some flickers of flame inside. And that's because there's only a certain amount of oxygen that's in there, okay? When it expanded, it used up the oxygen that was there when it ignited. It used up the oxygen, pushed it out, and with all the air coming out, some other air comes in to fill in that space, and some of that had some oxygen, so it could reignite some of the alcohol vapor that was still left inside. So that's our whoosh bottle. And let's think about using a little bit, let's put a little bit more with fire. So this is something that I'm going to do here. For you at home, only use fire in the presence of an adult with their supervision and permission. But we're going to try and use some science to look at how things burn with our Lycopodium powder, with our whoosh bottle. But now let's think about how we can use science to put fires out. So let me grab a candle here. So I've got my candle, I've got a beaker here, and I have my materials that I had from before. Let me turn the lights back on a little bit for this. All right, so let's look at our flame. So let me light my candle. Candle is not lighting. Here we go. Let's try it again. Let me grab a different one. There we go. There we go. All right. So now I've got a flame here. Let's make sure we can see that. There we go. So there's my flame on my candle. And what we're going to do is we're going to mix some materials together to make an invisible fire extinguisher. Okay. So the only things that I need to make this invisible fire extinguisher are, I'm going to use 2 different cups. I'm going to use some vinegar, and I'm going to use some baking soda. Okay, some stuff that we've been using already. And so first thing I'm going to do is I'm going to take some baking soda and put it into my beaker. Okay, so there we go. Got a little bit of baking soda in my beaker. Actually, let me do it in this larger beaker. I'm doing a larger beaker. Okay. So I got some baking soda in here, and I'm going to add some vinegar to it. And we'll see what happens when we do that. So let me take some vinegar here. All right. So as we do this, you might have done this experiment before. If you've ever, maybe made one of those volcanoes or something like that, or you maybe just mixed some vinegar and baking soda together before and seen what happens. So as I mix these together, again, I want you to make observations. Notice what's happening with our in our jar here, and then we'll create our invisible fire extinguisher. So I'm going to mix these together. So my baking soda, my vinegar, put it in there, and we see that it's creating some bubbles, right? It's creating this big fizzing in there. So right now it's creating my invisible fire extinguisher. So what I'm going to do is I'm going to pour not the liquid that's in here, but my invisible fire extinguisher into my other glass. Notice there's nothing in here already. I'll pour it in. Okay. And so now right here in my glass is my invisible fire extinguisher, and I will use it to put out my flame. There we go. So we're able to create our invisible fire extinguisher with just baking soda and vinegar. So let's think about what's going on here. Let's investigate what is happening in this. So let me pour this out, and we'll redo it and talk about the science that's happening here with it. So we're going to put our baking soda in, and let's think about states of matter. Let's think about solids, liquids, and gases. So in this case, our baking soda is a solid, right? So this powder here, I'm going to put it here into my jar. It's a solid. And our vinegar is a liquid, right? It's something that can flow and takes the shape of the container. When I add it to the baking soda, we're creating a third state of matter. We're creating a gas. So a gas is like the air around us. And when we do it, you might have noticed that it was creating all these bubbles, right? And so the bubbles is the reaction of vinegar and baking soda together. They create this gas called carbon dioxide. We talked about carbon dioxide earlier, right? And so the bubbles, inside the bubbles is a gas, not the surface of it. That's kind of more of the liquid. But inside of it is a gas, and that's what's being created. Now, the cool thing about carbon dioxide is that it's heavier than the regular air around us. So it's more dense. That means that it can sit down lower than the other air. So when it's creating the carbon dioxide here in this container, those bubbles are created, they pop. And so that carbon dioxide gas fills the container. It just kind of sits there lower in the container than the rest of the air around it. Eventually, it would spread out and mix with all the air. But for a little while, it just sits there. And I can pour it, since it's heavier, I can pour it into my other container. I'll be able to pour that gas into here, and it'll fill it up. So this is completely filled with carbon dioxide gas. And then since it's heavier, I can pour it onto my flame. And so let's talk a little bit about the flame itself. So fire needs a few things to stay fire, right? It needs the fuel. In that case, the fuel is the wax that's here in the candle. It needs oxygen. So oxygen is in the air around us, and it needs that oxygen to be able to burn, and it needs heat. And so if we take away one of those things, then our fire goes out. So if we took away the fuel, if your candle burns all the way down and all the wax is gone, it'll go out, right? There's no more fuel. If you take away the oxygen from it, then it'll go out. And so in this case, we're taking away the oxygen. So it's not just that it needs air, it needs oxygen. So we can put a different type of gas around it, and that will put it out if it's not oxygen. So if we take carbon dioxide and put it on there, it smothers it. It pushes all the oxygen away, and it just leaves the carbon dioxide around it, which puts the flame out. So let's do it one more time, now that you know what is happening. And so let me light my candle again. Oh, here's my lighter. So we'll light the candle, and we'll create our invisible fire extinguisher. So again, we'll mix together vinegar and baking soda to create carbon dioxide. Here we go. all those bubbles are carbon dioxide. It has carbon dioxide in them. They're popping. As they pop, then it's just leaving carbon dioxide here. We can't see it. It's an invisible gas, but this is just full of carbon dioxide. So I'm going to take that carbon dioxide that's sitting there and pour it into this one. There's nothing in here right now. So I'll pour it in, not pouring the liquid, just pouring the carbon dioxide. And so now this is full of carbon dioxide gas, and I can pour it onto my flame and put it out. And there we go. We can use science to be able to create a fire extinguisher. There we go. And so we've got a few more minutes left. And for this, I want to show you, with my remaining time, one other fun activity. And this one isn't so much about chemistry. This one's a little bit more about physics, actually, and thinking about how we can create things using different amounts of pressure. So let me grab my container here. So I have here goes my water jug. So I've got here a 2-liter bottle, and it has in it a thermometer. Okay, so this is just a little thermometer, so I can tell what the temperature is. And we can tell what the temperature is by the number that is showing up. And I don't know if we can see that on screen there. But right here, it's showing these numbers right here. So it's kind of showing a 22 and a 24. So that is in Celsius. And so it means it's about 72 to 75 degrees in this room. It's a little bit warm in here. And what we're going to do is I'm going to add some alcohol into here. And we'll see what happens when we change the pressure of our bottle. So on top of my bottle, I've got this thing called a fizz keeper. So I can pump air into it and I can make it more pressurized inside the bottle here. So let me put a little bit of alcohol in here. Pour some alcohol in there. There we go. So we've got some alcohol in here, just like we did with our big water jug, right? So I've got some alcohol. I'm shaking it around. It's sealed. And so that alcohol, some of it's still a liquid in there, but it's turning into a gas. It's turning into a vapor. And what I'm going to do is I'm going to pump it up. So right now there's some air inside there. I can squish the bottle, right? I can compress it right now, but I'm going to pump air into it. And so what that's doing is it is pressurizing it, making it a lot more air inside, a lot more pressure inside. And we'll notice that as I do that, if I try and squeeze the sides, it's a little bit harder to squish in the sides because there's more air in there. And we can also look at the thermometer here and see what's happening to it. So we can see, there we go. So you can see the 24 more bright now, and the 26 is starting to light up. So it's getting hotter inside. So just by pushing more air in there, it's making the temperature go up inside the bottle. And so what's happening is that normally when there's some vapor, some air, some gas in there, those molecules, those atoms, they're bouncing around inside, they're bumping off of each other. And it takes a little bit of space for them to hit other ones because there's not as many in there. As we add more pressure, as we add more air in there, they bump into more of them. And so that is what's increasing the pressure because there's more activity of things hitting each other. So those molecules are hitting each other more and more because there's more of them to hit. And so the temperature, we can see now the 26, let's see if we can see that on the screen. The 26 is a lot brighter now. And so it's getting up to about 76 degrees Fahrenheit, yeah. Okay, and now I try and squeeze the sides. I can barely compress the sides at all. And so what I'm going to do is I'm going to open up the top, release the pressure, and we'll see what happens inside the bottle when we do that. Okay, here we go. Ready? 1, 2, 3. There we go. And so inside, what does that look like? Huh? It looks like it might be something you would see up in the sky, right? It looks like a cloud. We just created a cloud in a bottle. And that is how clouds are created. It's changes in temperature, changes in pressure. In this case, we had it a really high pressure, made it into a really low pressure, and that made the temperature go down really quickly. So you can see on here, so it's no longer up at the 26, the 22 and 24 lit up. So it went down about 4 degrees, 3 or 4 degrees, just by releasing the pressure. And so that rapid change in pressure, that rapid change in temperature made the alcohol vapor turn back into a liquid, and it's suspended in the air. So that's what clouds are. They're suspended liquid in the air. So are there any questions that folks have had as I've been talking? If not, we are almost out of time here. And so I want to really thank you guys for coming. This has just been a show of some bunch of different types of demos for you about chemistry, a little bit about physics. And all of these different things that I've been doing are things that scientists work with. So maybe not doing the demos all the time, but they'll work with things like pH and acids and bases. They'll use them for different things. They'll look at the rate of reaction of how things are mixing, if it's really quickly or really slowly, how that can affect what it is that you want it to do. Meteorologists are really thinking about pressure and temperature and how that affects the atmosphere, so they can predict if there are going to be clouds, if there's going to be rain. So all of these are things that scientists and engineers use. The principles that I showed you today are ones that they use all the time, and used in so many different ways and in so many different types of jobs out there. Thank you guys so much for having me. I appreciate your attention. Thank you so much.
No, well, thank you very much, Kevin. We do appreciate you sharing your time and showing us more into the world of chemistry and physics. And so just some of the questions that we want to leave off on was, how can kids do more awesome, cool experiments like this with Explora? And, are most of these experiments, can they be done at home? And, finally, what are just some words of encouragement that you have for those who are attending today?
Yeah, so a lot of these things that I did with you are ones that you can do at home. Of course, some of the ones with fire, maybe not so much. You can do the one with the candle with the supervision of a parent or guardian. The cabbage juice one is definitely something that you could do at home. So just boil a purple cabbage in some water, save that water and use it, test out different things in it, try out some things around the kitchen, see what color it changes that liquid to. So yeah, some of these are definitely ones that you can do at home. In working with Explora, we have lots of different programs. So if you go to explora.us, that's our website, we have different workshops, activities, programs for folks to do, but also you can just come to the museum. We have lots of fun activities, hands-on activities that you can do. We also come out to schools. So maybe we'll be coming out to your school soon, to your classroom. So keep an eye out for us. And lastly, some words of encouragement, just keep investigating. The world around us is so fascinating. So just pay attention to it. Notice the things that are happening around you and try and figure out why it does. So sometimes that's stuff that you can just test out on your own. So for example, with the cabbage juice, just test out some different things and try and figure out what things are acids, what things make it turn pink. And that's how we know it's an acid, what things make it turn blue, and that's how we'll know it's a base. So you can find out if some things are either those, or if it's neutral, meaning it's not an acid or a base, it's kind of in the middle. And so you can test out lots of different things that way. So just keep exploring and keep discovering, just like the title of this is, right? Discovery Fest, discover different things.
Awesome. Well, Kevin, look, I'd like to, again, just thank you for your time. Thank you and your team at Explora for joining us today. And for those of us who are watching, I encourage you to be a part of our STEAM Fest Discovery Festival, where you could kind of use what you're learning today and enroll in our science experiments competition. So awesome. Thank you very much. And we will definitely continue to explore and to create.
Bye, everybody.
All right. And so we'll go on ahead and conclude by thanking our sponsors who were able to make Discovery Fest exhibition today and all of our previous exhibitions possible. And thank you very much for your attendance.